we're going to use contour plots to be able to calculate average rate of change and the path of steepest descent. So let's say that this is my contour plot. So this is a representation of some three-dimensional surface that's been flattened down to fit onto the chalkboard. You might not be able to see it on the video, but each of these contour lines of this contour plot have a number attached to them. So this is telling me this outermost line has a value of 100, meaning pretend that we're on a mountainside and our height or our z-value is equal to 100 exactly along this curve. That's one reason why we call the lines in the contour plot are called level curves. Why, you ask? Well, because it's a curve, it's some curvy thing along this flat plane, and it's level, meaning that the height is exactly the same all the way around here. And if I were to try to visualize what this contour plot is telling me, it looks like my heights get higher and higher as I go this way, and they also get higher and higher as I go this way. It's like a mountainside that has a peak up here at 600 and then a smaller peak over here at 500. And if I wanted to, each of these curves are tracing out a slice of this mountainside. If I were to draw what these slices are doing. This isn't exactly right. I don't think I have the exact right number of slices. But the idea is that when I slice this, if I were to take some knife and slice this terrain, the level curve would be given by all of the places along here that are exactly the same height. If I want to know the average rate of change given this plot, that's just asking how fast am I ascending? And the equation for average rate of change is given by the change in vertical height divided by the change in horizontal distance. So I'll write average rate of change is given by my change in height given by my change in horizontal distance. So for example, if I were over here at some point A, and I want to know what's the average rate of change as I go to a point B, really what I'm asking is, I want to know what the change in altitude is, or the change in height divided by the change in horizontal distance. We see that this point A is very close to the 200 curve, so I'm going to say that the height at point A is maybe 180, I'm estimating. And point B is close to the 300 curve, so the height at point B is approximately equal to 280, meaning my displacement, my vertical displacement from A to B is 100 units. I'm not talking about walking around the mountainside, I'm talking about how much is the difference in height at points A and points B. And the horizontal distance is computed by a Pythagorean theorem. I would need to know the location of point A and the location of point B, and I could use Pythagorean theorem to find the distance between them. So let's say that in terms of x and y values, maybe my x and y value for A is at, I guess I'd have to have some reference point. Let's say that it's over -1 in the x direction and up 3 in the y direction, whereas my point B over here is over -4 in the x direction and up 7 in the y direction. My horizontal displacement, I'm going to need to use Pythagorean theorem to find the distance between these 2 points. The distance between these 2 points is going to be given by the difference in the distance between the x coordinates, which in this case the difference between -4 and -1 is 3. And the difference between the y components is 3. The y component is 3 and the y component is 7, so the difference between these 2 components is 4, which means that the distance between these 2 points is 3 squared plus 4 squared, all square rooted, which is just 5. I chose a 3, 4, 5 triangle. So what does that mean in terms of average rate of change? The average rate of change between points A and B is given by the total change in height, which we decided point A is at about 180 and point B is at about 280. Maybe I should have said 70 before. So the vertical displacement is 100 and the horizontal displacement is 5. And that means that the total displacement, or the average rate of change, is going to be 20 vertical units per horizontal unit. Hopefully that isn't that groundbreaking of an idea. Another thing that we want to be able to do, given these contour plots, is to look at paths of steepest descent. So let's say that we were starting at point A, and we wanted to know the steepest way to hike up to get to the top of the mountain. What is the steepest way? It would mean that I would have to get to the next level curve as efficiently as possible. If I meandered over this way to get to the next level curve, it would have taken me a longer amount of distance in the xy plane to be able to cover the same amount of vertical height. So the shortest or the steepest descent is going to be the direction that is exactly perpendicular to each of these level curves. Because if I went off at some crazy angle, it would mean that I was taking a longer amount of distance to cover the same amount of vertical distance. So that's what the path of steepest descent. There's no formula for that. It's just visualizing the fact that if I want to get to the top of the mountain as fast as I can, I should probably get to the next level curve as quickly as I can, or as in as short amount of distance as possible. So the final topic that I want to talk to you about is level surfaces. So we've talked about graphs of multivariable functions where we only had 2 inputs into the function. And I want to talk about what happens when we have a graph where we have 3 points, or a point in R3 is our input into the function. And let's say that I have the function x squared plus y squared plus z squared. And I want to get an idea, what does this multivariable function whose domain contains points in R3 look like? And the tool for being able to analyze that is to use the idea of level surfaces. In our 2-dimensional space, we talked about level curves. Level curves are what make up our contour plots. They're the curves that are exactly level for a given z value, or our output value. Level surfaces are going to be exactly analogous. So I'm going to set my f of x, y, and z equal to some constant value. And when I set it equal to some constant value, it's going to trace out some surface. And for all of my different output values, it'll trace out different surfaces. In this case, let's look at what happens when I set f of x, y, and z exactly equal to 0. I get the function 0 is equal to x squared plus y squared plus z squared. This is a really boring level surface. My level surface is going to be represented by some figure in 3-dimensional space, and we know what this level surface looks like. Here's my x, y, and z coordinate system. This is a level surface, and it looks like a sphere of radius 0, centered at the origin. So what's a sphere of radius 0 centered at the origin look like? It's just the point 0, 0, 0. The only solution to this equation is when x, y, and z are exactly equal to 0. So this was when I let my level surface f of x, y, z exactly equal to 0. Now what happens when I let f of x, y, z exactly equal to 1, for example? So in this case, 1 would be equal to x squared plus y squared plus z squared. So my inputs are going to be, points in R3, And for this particular level surface, when I set my function exactly equal to 1, I get a level surface that's a sphere of radius 1. And my next level surface, you can see where this pattern is going, 2 will be set equal to x squared plus y squared plus z squared, which gives me a different level surface of radius square root 2. And then so on and so forth. If I keep thinking about these level surfaces, it'll be like a bunch of nested spheres. Notice that I'm supposed to be drawing this in three-dimensional space, so I'll have an innermost sphere, and then a sphere that's a little bigger, and a sphere that's a little bigger. And they're called level surfaces because everywhere along this sphere, my output values are exactly equal to the same thing. So in this case, every point around on this outermost sphere, those points, when plugged into this function, all have an output value of 2. One way to think about what this is actually describing would be something like a temperature function. So let's say I'm in a room, and the temperature of the room is given by this function x squared plus y squared plus z squared. This isn't a very realistic example, but it's something that could be talked about. And it means that in spherical shapes within this room, all of the temperatures at that spherical shape are exactly equal to one another. So I could have some sort of heat sink right at the origin. So right at the origin, the temperature is equal to 0. And in spherical waves emanating outwards, the temperatures are exactly equal to one another. And the temperature gets bigger and bigger and bigger as you move outwards, away from that heat sink centered at the origin. So that's the idea behind level surfaces. And we will not tackle them in great detail, but it's an important tool to be able to have to think about multivariable functions that have more than 2 inputs.